in the last session, we talked about central bank digital currencies. We talked about using the public key as the identity and then allowing people to just create their own accounts. And I just want to mention here again that anyone can create as many accounts as they wish, because creating an account is basically the same as generating a key pair. And we saw key generation mechanisms before. You can generate as many keys as you like. And then we saw that we use digital signatures for proof of consent. We saw that the central bank creates money. We had this gossip protocol that was used for messaging in the whole network. It was used to send transactions, but also to send confirmations or verifications from the central bank that a particular transaction is finalized. And then we saw transactions. We saw the different parts that a transaction has. We talked about this UTXO model, where basically every transaction has a bunch of inputs, and the input to this transaction is a bunch of unspent outputs from previous transactions. Okay. And we talked about the constraints that every transaction should satisfy in order to be valid. And we talked about the most important problem, which was double spending. And we basically said that our solution to double spending is a consensus mechanism. So as long as everyone can reach a consensus about the history of all the transactions that have taken place, then we have no problem with double spending, because in this consensus, I will have at most one of these two transactions if they're both double spending the same coin here. And by the way, sometimes I just use the word coin instead of output or unspent output of a transaction. So whenever I say coin, I just mean the output of a transaction. And yeah, so our solution for reaching consensus was to have a central bank. And we basically said that the central bank keeps track of the authoritative list of transactions. So I have a list of transactions that is maintained and published by the central bank. And this is the list that everyone agrees on. So a transaction is pending unless it's added to this list, and it's only finalized when it is added to this list. And only the central bank can add to this list. And we said, as before, every transaction in this list will have a pointer to the previous transaction and also the signature of the central bank. So that's how you make sure that only the bank can add these. And then these verifications, which are basically the transaction, the pointer to the previous transaction, and bank signature, they're also published on the network using the gossip protocol in the same way that transactions themselves are published. So based on this, we said that every node other than the bank keeps track of two different lists of verification and two different lists of transactions. So the bank only keeps track of one list, and the bank's list is basically the most important list and the one that everyone will follow. But everyone else will have their own list, which is the list of all the transactions that they have heard about. But they will also have the bank's list, which is the list of all the transactions for which they have received verification from the bank. They have received the bank's signature. And again, from everyone's point of view, these are the transactions that are finalized. So these are finalized transactions, but these are just pending, and they're waiting for the bank to decide if they're going to become finalized or not. Now, of course, the whole point of this course is decentralization, and this is defeating the main purpose. I have a central bank. Nothing can get more centralized than that. So I have some improvements over the current banking system in terms of privacy. So if you compare this with how, let's say, your digital banking app works, at least you have a high degree of privacy here. For example, if you want to send money to me, I can just create my own account. I can create my own public key and private key, and I just give you my public key and you send me money. And even though the central bank is the one that has to sign on that transaction, they don't really know my identity, right? So there is some level of anonymity. It's not perfect, because if I later on go and spend that money somewhere let's say I go to Starbucks, I buy a coffee, maybe they see my face and they also see the transaction that paid them, so they can connect my face to my blockchain identity, and that's like a connection between the real world identity and the blockchain identity, and I wouldn't be very happy about that. So it's not perfectly anonymous, but at least the idea is that you're transacting with your public keys and you can create as many public keys as you want. So it's also not directly connected to your real world identity. So it has that kind of merit. But on the other hand, we saw that the bank can basically do censorship. So for example, suppose that tomorrow the bank decides that I'm not going to allow any transactions that have some particular message in them, or I'm not going to allow any transactions that are above $500. They can do that because a transaction is finalized only if the central bank signs on it. And the central bank can just decide, I'm not going to sign this particular transaction, right? Or maybe the central bank, again, hates you and they know, let's say, one of your public keys for some reason. And you have a lot of money in that particular public key, in that particular account. They can freeze your account in the sense that whenever you're creating a transaction out of that particular account, they can just say, hey, we're not signing this, we're not adding it to the list of finalized transactions. So basically all the money in that account will be frozen. Now, of course, this doesn't affect consensus. Everyone on the network reaches consensus about who owns what. So everyone on the network agrees that you own that money, but you cannot spend it. So you see, there are these problems with having central banks. And again, we're going to have a homework about this. But today we're going to talk about how to make it decentralized. So this is the idea, how to achieve decentralization. Now we're going to keep some of the same architecture that we had in the centralized case. So I'm going to say that every node is keeping track of 2 sequences of transactions. Every node is going to keep track of, let's say, finalized transactions and pending transactions. And pending transactions are, again, all the transactions that this node has heard about, but finalized transactions are the ones that are, well, finalized, it's in the name. But instead of saying that there is only one central bank that can add to the finalized transactions, I want to say everyone can add something to the finalized transactions, okay? So this is actually the idea of a blockchain, and I'm just going to define a blockchain here, and then I'm going to go forward showing you how to use it. So a block is just an array or a sequence, or a list of transactions, okay? And of course, there's also some metadata. So it's a list of transactions. It can also contain some extra information. We don't care about this extra information at this point. And then a blockchain is just a linked list of blocks. Okay, so a blockchain is something like this. I'm going to have B0, B1, so on. And these are each blocks. And each one of these blocks also has a pointer to the previous block. And again, remember, we use hash pointers. So when I say B1 has a pointer to the previous block B0, all that means is that B1 contains the hash of B0. And this is part of the metadata that I told you. So every one of these blocks is going to contain a bunch of transactions. Actually, block 0 is empty, so it doesn't contain any transactions, let's say, but block 1 contains a bunch of transactions. So maybe transaction 1, transaction 1, 2, so on. Block 2 contains a bunch of transactions. So, and of course, every block also contains a pointer to the previous block, which is just a hash pointer. So generally speaking, I have block n here, and it has a pointer to the previous block. So it has the hash of block n minus 1. So this is what I call a blockchain. Now, this is very similar to what we had here, the list that the central bank kept, except that here, every element of our linked list was just one transaction. But in this one, I'm saying that every element of my linked list is a block. So it can have more than one transaction. Now, this is for really small technical reasons. The idea is that I want to have fixed size blocks. So usually I also put a block size limit. So I say a block is a list of transactions and metadata with some limited size. Okay, and the limited size is almost 1 megabyte in Bitcoin. Let's say 1 megabyte. Okay, so here's what I'm going to do. I'm going to say every node keeps track of two things. Every node on the network keeps track of two sets or two lists of transactions. So there is a set of pending transactions. And in Bitcoin, actually, we call these mempool. So the mempool is the set of all pending transactions. So these are the transactions that this particular node has heard about, but this node is not sure if these transactions are part of the consensus. Okay. And it's also going to keep track of a blockchain of finalized transactions. So whenever I'm talking about the blockchain, I'm just talking about this node's copy of the blockchain. And these are all the transactions that, from the point of view of this node, are considered finalized. Now, of course, we want this blockchain to be subject to consensus. So we want everyone to have the same blockchain. And again, remember, a blockchain is just a linked list of blocks, and each block is itself a list of transactions. So this is ultimately a list of transactions. Okay. And any transaction that is on the blockchain is considered finalized from the point of view of this node. Now, again, I can have a centralized solution, and I can say that I have a central bank that maintains the blockchain. And I can say you can add a block to the end of the blockchain only if that block is signed by the central bank, right? So if I do that, I will have basically the same setting as in the previous session, with the only difference that I'm chaining blocks instead of chaining transactions. But that's, of course, centralized. And remember our very first definition of decentralization. We wanted to say that everyone on the network has the exact same permissions. So if anyone can add something to the end of the blockchain, everyone should be able to do it, right? So I want a decentralized way to add stuff to the end of the blockchain. But I also need to ensure consensus. I need to ensure that everyone on the network agrees about the contents of the blockchain, because that's the whole point of having a blockchain. Otherwise, I could just have my mempool, right? Now, this seems contradictory, because if I have thousands of nodes on my network, and let's say I have this blockchain and everyone can add the next block, it's very probable that a lot of them would add, right? So maybe this is what's going to happen. Maybe I have my blockchain, and then maybe two different nodes on the network, two different people try to add alternative blocks for block n plus 1. So someone says, I want to add this one. Someone says, I want to add this one. Maybe it's even more than two. Who knows? Okay. Now, if everyone has the same permissions, at this point, I don't really have a way of saying that this particular block is valid and this one is invalid, because, well, the people who created them are supposed to be equal. So I cannot just say I prefer this one over this one arbitrarily, right? And also, by the way, this is what we call a fork. So a fork is when you have, well, again, a fork, when you have different branches in your blockchain, when people are proposing different blocks. And of course, this fork can continue. I might have like something like this. Maybe someone proposes a block here. Maybe I have a fork within a fork. It can get crazy. Okay. So generally speaking, I want to avoid forks. I want to make sure that if a lot of people publish block n+1, they publish, let's say, their own candidates for what block n+1 should be, everyone on the network eventually reaches a consensus. Everyone eventually agrees what the correct block n+1 is. So that's what I want to do. Now, this is the part where we're going to see one of the really genius solutions in Bitcoin, and this is called proof of work, or POW. Okay. Here's the idea. Everyone should have the same permissions, but just allowing everyone to add the next block would create a lot of forks. So we say, okay, let's give the same permissions to everyone, but let's make it really hard to add a new block. Let's say that you can add a new block only if you have done a lot of work, only if you have done a lot of computation, okay? So you can add a new block to the blockchain only if you have performed a lot of computation. Now, this is nice in theory, but how do we actually achieve it in practice? So suppose that I say you can add a new block if you have calculated trillions of mathematical equations or something like that, right? Suppose that I do it. How do I prove to you and how do I prove to everyone on the network that I have done it? So I somehow need to find a mathematical puzzle such that solving the puzzle takes a really long time. But when I solve the puzzle and give you a solution, checking whether the solution is correct should be really fast. If I can have that kind of puzzle, then I can use it in proof of work. I can say, okay, whenever you want to add a new block, you cannot just create a bunch of transactions and a pointer to the previous block. You have to also prove to everyone on the network that you have solved the puzzle. So you have to give the solution to this puzzle as part of your block. And then everyone on the network would verify that that's a valid solution to the puzzle. But really importantly, verification is going to be fast. So they can verify it almost instantly, even though finding a solution was really hard. So that would prove to them that you've done the hard work of finding the solution. It would prove to them that you've done a lot of work. It's proof of work. Okay? That's the whole idea. So we need a puzzle. And we need this puzzle to have two properties. We need it to be hard to solve. So it requires a lot of computation to solve. But we need it to also be easy to verify. So if I give you a solution, it should be really easy to check that this is a valid solution. And it turns out we have something like this, and we can create this using hash functions. Okay? So this is what we call hash-based proof of work. or sometimes it's called hash puzzles. The idea is this. Let's say that I have a cryptographic hash function. So let's fix a cryptographic hash function H. So for example, let's say we're doing SHA-256, which is a very famous hash function. Actually, Bitcoin does SHA-256 twice, but it doesn't really matter. It can be any hash function. Okay. Now, here's the thing. If I give you some particular value, if I give you some X, it's easy to compute hash of X and you get Y, right? But if I give you Y, it's really hard to compute an X such that hash of X is Y. So you see, we kind of have the same situation that we like to have here. We have something that is hard, but it's easy to verify. And that's inverting a hash function. But I'm not just going to invert a hash function for a particular value. This is what I'm going to do. Let's say my hash function takes some input of arbitrary size and gives me an input of size 256. Okay. I'm going to choose a difficulty level. So I'm going to say, let us choose some number D. And this D is going to be between 0 to 2 to the power of 256 minus 1. Okay. And then this is the puzzle that I want you to solve. The puzzle is to find some value, find some X, such that when I take the hash of X, it's less than or equal to D. Okay. Or actually, sometimes it's easier if I say that D is from 1 to 2 to the power of 256, and then I say that this hash is less than D. Okay. So I have some number D, and I have a hash function. I'm not telling you to just invert the hash function. I'm just telling you find some value X such that when I compute the hash of X, this hash is less than D. Okay. Now, remember when I was talking about hash functions, I said that one other property that we will come back to is puzzle friendliness. And we're going to talk about puzzle friendliness right now. So let's say I give you this particular puzzle, and let's say that your hash is SHA-256. How can you solve this? How can you find the value of X such that its hash is less than D? Here's what you can do. You can just try random values of X, right? So this is one solution. It's going to say just try random values of X. What does this mean? It means that I'm just going to have an infinite while loop. I'm going to say forever repeat this. Choose some value of X randomly. Let Y be the hash of X. And if Y is less than D, return X. Okay. So I'm just going to keep trying different random values of X until I find a value whose hash is less than D, until I find a solution to my puzzle. And then I'm just going to output this solution. Okay. Now, this will probably take a lot of time, right? Generally speaking, so let's say I try n different values. Okay. And let's simplify everything. And let's say that this hash function, even though we know hash functions are not one-to-one, let's just say that it acts like a one-to-one function, because honestly, we said that it's hard to find collisions in a hash function. So even though mathematically it's not a one-to-one function, from our point of view, it's pretty much like a one-to-one function. I cannot find a collision, right? So if I try n different values, what is the probability that I find a value that is less than d? Okay, so every time that I find any value, the probability of success after one try, like trying one value and hashing it, is exactly d over 2 to the power of 256, right? Again, and I'm also assuming that my hash function is acting like a random function, like a uniform random function. That's another assumption that is under the hood here. But generally speaking, if I try 1x, I'm saying I chose x randomly, I took the hash of x, I would expect this hash of x or y to also be a uniform random number. So it's a uniform random number between 0 and 2 to the power of 256. The probability that it's less than d is going to be just d over 2 to the power of 256. Okay? Now, so this means that probability of failure after one try it's just going to be 1 minus this, right? 1 minus d over 2 to the power of 256. Okay. So what is the probability of failure after n tries? So if I try n different random values, what is the probability that all of them fail? So each one of them has a probability of this much to fail. So the probability that all of them fail is just that number, d over 2 to the 256 to the power of n. Okay. So the probability that I succeed after n tries, probability of success after n tries, well, it's just 1 minus the probability of failure after n tries. So it's just 1 minus this whole thing. 1 minus d over 256 to the power of n. Okay. But generally speaking, this d is usually really small. Okay. So we will see some of these values of d for Bitcoin later on in this course. But if I assume that this d is really small, I can kind of simplify this and I can do a bit of a hand-wavy analysis, which is not as exact as this one. And I can say, if I try n different values, my probability of success is almost, well, I tried n values and every time I had a d over 256. So n times d to the power over 2 to the power of 256. I can also have this kind of approximation. And generally speaking, this kind of approximation only works if d is really small, which it is in the real world. But the exact probability is this one, of course. But what does this tell you? In any case, it tells you that the more values you can try, the more random values you can try, the higher probability you have to be able to solve this puzzle, right? So here's the thing. Just trying one value gives you this probability of success. If you try n different values, this is your probability of success. But as n tends to infinity, this probability of success tends to 1. Okay? So the more hash values you try, the more likely it is that you would be able to solve it. So now here's the question. How much time would you need to solve this particular hash puzzle? So here's, again, the calculation that goes into that. Suppose that I want to solve this hash puzzle, and I'm just continuing to compute random numbers and taking their hash. The more hashes I can compute per second, the faster I'm going to be able to find the solution, right? So my probability of success in, let's say, 10 minutes, it's going to be proportional to the number of hashes that I can compute in 10 minutes. So the more hashes I can compute, the more probable it is that I would succeed in solving this puzzle. Okay? Now, this is also the property that we call puzzle friendliness. So what is puzzle friendliness? We said all of the cryptographic hash functions that we use are also assumed to be puzzle friendly. It just means there is no better solution for this puzzle than trying random values. Okay. Again, when I say there is no better solution, I don't mean it in a mathematical sense. I don't mean that someone has a proof that there is no algorithm that would solve this faster. I just mean that no one knows a faster algorithm. So for example, when it comes to this puzzle for inverting the SHA-256 hash function, or the Bitcoin hash function, which is just SHA-256 applied twice, no one knows a better way than just trying random values of X until you succeed. And that's why we say that this hash function is puzzle friendly, because no one can do anything better than that. Okay. So how do we put this proof of work into our cryptocurrency? So how to integrate proof of work in our cryptocurrency. Remember, I said that we're going to have a blockchain, and we want everyone on the network to reach a consensus about the blockchain. So I have this blockchain, and let's just assume that we have consensus about the first 10 blocks. So I have B0, B1, all the way to B10. And let's say that everyone on the network just magically agrees about all these blocks. We agree about the first 11 blocks, B0 to B10. And now there are a lot of different people who would like to add B11. And maybe they have different blocks that they want to propose as B11, right? So here's what we say. We say that in order to add the block, you have to solve the proof of work puzzle. Okay, so in order to add a new block, actually, let me just remove this number. And instead, let me just say that we agree up until Bn, and everyone wants to add Bn plus 1. So in order to add a new block Bn plus 1, you should solve a proof of work puzzle. Okay, so I'm going to be more specific about what I mean here. And this goes back to the metadata that I told you we're going to save in our blocks. So I told you that every block is not just a sequence of transactions, it also has some metadata. And that metadata is going to contain the pointer to the previous block, but it's also going to contain the solution to the proof of work puzzle. Okay, so this is how my block looks like. So this is what I'm going to put in my block n+1. Okay, it's going to have a pointer to the previous block. And remember, we're using hash pointers. So I'm going to have hash of bn here. Okay, this is just a pointer to the previous block. That's fine. I'm also going to put a public key here. And this is the public key of the person who's proposing this new block, public key of the proposer. Okay. Actually, we usually use the word miner for the proposer because the person who's proposing this block is the same person who's doing the proof of work puzzle, who's solving the proof of work puzzle. So we usually use the term mining for solving this proof of work puzzle. And the people who are doing this, we call them miners. So this is just the public key of the miner, whoever is proposing this block, right? And this block is also going to have a bunch of transactions. So it's going to have transaction n+1, transaction n+1, blah, blah. And these transactions, they're usually put in a Merkle tree. Again, that's just so that we can search for transactions easily. But you don't have to. You can, I mean, if you're creating your own cryptocurrency, as long as you have a sequence of transactions here, you can use whatever data structure you like. But usually it's a Merkle tree. So I have a Merkle tree of transactions. Again, you can just decide that you don't like Merkle trees. You can say, I want to have a linked list of transactions. You can say, I want to just have an array of transactions. You can use whatever data structure you like. The important point is that every block will contain some transactions. Okay? And then it's going to also contain a nonce. Okay? And let me actually call this X. So this X, it's called a nonce. And it's actually also the solution to the proof of work puzzle. Okay? So this is everything that I'm putting into my block. Now, honestly, in Bitcoin, there is a bunch of extra metadata. There is a timestamp. You have all sorts of other things. But for now, let's say these are the things that I have. These are the things that we really care about in this course. You can, of course, based on your needs in your particular cryptocurrency, add as much metadata as you want to every block. Okay. So here's the part where the proof of work puzzle comes in. So I say for the block to be valid, for bn+1 to be valid, the hash of the whole block, hash of the entirety of bn+1 should be less than my difficulty threshold D. Okay. Now, people usually think of this as the number of zeros that I should have at the beginning of my hash. So it's like my hash is going to give me 256 bits. I might say that, well, I want to have 32 zeros at the beginning of my hash value. And that would correspond to saying that, roughly speaking, you have to compute 2 to the power of 32 different random hashes before you're expected to reach a solution. Okay? But this particular architecture is actually really important. I want the hash of the entire block, so including all of these transactions and metadata and everything. So if I take the entirety of block n plus 1 and I take it as a string, I want the hash of that string to be less than d. Okay. Now, of course, solving the proof of work puzzle is just as before, because all of these other parts are fixed, right? So if you're a miner, if you're someone who wants to propose a new block, all of these things are already there. And you of course have no control over the hash of the previous block. You're just trying to extend the blockchain. You have chosen your own public key. Of course, you can choose several different public keys, but anyway, at some point you make a choice about your public key and you make a choice about the transactions that you want to put in your block. The thing that you use mainly for proof of work is X. So you're just going to choose different values of X, and every time that's going to give you different structure or different values for block n plus 1. And if you choose X randomly, this is also random, so the hash value is also random. So I want to say that this random hash value is less than d. Now, the idea is that this is a hard puzzle, so it's actually helping us against forks like this. Because every time that a new block is proposed, only blocks that satisfy the proof of work puzzle are considered valid blocks. Okay. And by the way, just like before, my blocks are also subject to being published using my gossip protocol. So when I create a new block, when I create a valid new block as a miner, when I find a solution to the proof of work puzzle, I just publish this block on the whole network. I just tell all of my neighbors about this, and then they will verify that the block is valid. They will verify that it actually solves the proof of work puzzle. And if all the checks pass, they give it to their neighbors and so on. And at some point, everyone in the network would know about it. Okay. So this is our solution against forks, or our defense against forks. Is that this kind of situation is now highly unlikely, right? So if I take this figure that I had of a fork, what does this figure mean? It means that at some point, 3 different miners, 3 different nodes on the network, solve the proof of work puzzle at approximately the same time. And I say approximately the same time because we have the problem of network delays just as before, right? Remember, this was actually the whole reason we had double spending, because our network has some non-negligible delay. So remember, when we wanted to do double spending, we would just publish one transaction on one side of the network and the other transaction on the other side. And some people would hear about the first transaction first, and some people would hear about the second transaction first. Now, the same thing can happen with blocks. If 2 people find valid blocks at the same time, so let me give these blocks some name. So I'm going to call this Bn plus 1. I'm going to call this one Bn plus 1 prime. And this is Bn plus 1 double prime. Right? So if this kind of thing happens, some people in the network will hear about Bn plus 1 first. Some people will hear about the primed version first. Some people will hear about this one first. And of course, you want to only extend the end of your blockchain. So if you've first heard about this one, if you first heard about this part of the fork, this branch of the fork, you would think that this branch is invalid. If you have heard about this branch first, you would think that the first branch is invalid. So it seems like we're going to have the exact same problem that we had before, except that before we had this problem with transactions. We had the problem of double spending with transactions. Some people heard about transaction 1 first. Some other people heard about transaction 2 first. But now I'm going to have it with blocks. Some people are going to hear about the first proposed block first, and some people are going to hear about the second proposed block first. Okay. But importantly, anyone could create a transaction. I could create a transaction at any time, and it cost me nothing to create a transaction, right? The costs of creating a transaction are negligible. I just needed to create a signature, right? Constant amount of computation on my own machine. Very cheap, basically free. But now, if someone wants to create a valid block, the valid block has to also include a solution to proof of work. It has to also satisfy this constraint. So it's really hard to create valid blocks. It takes a lot of time. It takes a lot of computation. It's expensive. I mean, we will talk about this later on. You need a lot of really expensive hardware, and you need to pay a lot for electricity, because actually the number of hashes that you have to compute, at least on Bitcoin, are insane. So it's very unlikely that two people find solutions at the same time, or at approximately the same time, within the delay of the network. And the delay of the network is like, what, 5 seconds, 10 seconds at most? Or let's be really generous, and let's say the delay of the network is 10 minutes, right? Even within 10 minutes, it's very unlikely that two people find a solution at the same time. Okay? So that's what we're going to do here, but that's not enough. So it's not enough to say that it's unlikely that our consensus breaks, because maybe it does break. What if we are really unlucky and 2 people or 3 people or so on find solutions at the same time? So what I've said until this point is that forks are unlikely, but we are computer scientists. We always do worst case analysis. We always say, yeah, well, maybe this thing is unlikely, but what if it happens? I cannot just say, oh, the probability of a fork happening is low, so I'm just going to hope and pray that it doesn't happen. If it happens in the real world, your currency will basically break into 2 different currencies. Some people would believe that this one, this block, is in the blockchain and has finalized transactions. Some other people would believe that this one is a finalized transaction. So we have to find a solution for forks. And this is the second thing that is really smart in blockchain, in the Bitcoin protocol. So what if a fork happens? And in this case, the Bitcoin protocol says that the miners can continue to extend whichever branch of the fork that they like. Okay, so let's say a fork has happened, and let me create a simpler fork with only 2 blocks. Okay, so let's say this has happened. We were unlucky. 2 different miners found a solution at approximately the same time, and they published it, and the whole network now knows about both of these solutions. So the miners for the next block, the miners who are trying to add block n+2, they get to choose. They get to decide which one they want to extend. So let me just copy this situation, put it here. So as the miner of the next block, I get to choose. I get to say, maybe I want to extend this one. Okay. And maybe we are still unlucky, and some other miner extends this one at the same time. Okay. As long as a fork exists, the blockchain protocol says that you can extend whichever branch of the fork that you want. But very importantly, as soon as one of the branches gets longer, that's the consensus branch. So the longest branch is the consensus branch. Or sometimes people use the word chain. They say the longest chain is the blockchain, is the consensus chain, right? So this is the longest chain rule in Bitcoin. So now I might get unlucky and I might have a fork like this, but as soon as one of the two gets longer, everyone on the network will just follow the longer branch, and they would say that this is the consensus blockchain. So everyone would ignore this one as soon as this one gets longer. Now, I might be unlucky, and maybe these two get extended again at approximately the same time. That's fine. I'll just wait for the next block. And maybe in the next block, this one gets longer. But again, as soon as one branch gets longer, everyone ignores all the other branches. So the longest chain is always the consensus chain. Okay, we're going to talk more about this next week. But at this point, we have all of the ingredients for creating Bitcoin.